we get into the properties of solids, let's review from last week. What are the types of forces that hold things together? Dipole, dipole. Ion, dipole, or ion, dipole, ion. Hydrogen bonding. The LDF, London dispersion force.
And dipole-induced.
Dipole-induced dipole. Yep. Now, for ionic bonds, ionic compounds, none of those are used if it's ion. Those are only strictly for molecular compounds, okay? Covalently bonded compounds. The first thing that we're going to talk about is we're going to compare liquids and solids. So, many properties of liquids and solids are determined by the strength and types of their intermolecular forces present. That's why they are the way they are. Because intermolecular attractions are broken when a substance vaporizes. We all hopefully know that vaporize means turn to a vapor or a gas. The vapor pressure and boiling point are directly related to the strength of these interactions. So, well, that was different. A familiar example of a change in state occurs when a liquid vapor evaporates from an open container. So we call this evaporation or vaporization when the liquid's molecules can escape and form a gas. We call this an endothermic process. Do you guys remember what endothermic means? The energy goes in. Yeah, we haven't talked about that yet this year, but from Chem 1, endothermic means it gains energy, which makes sense because, like, if you have to boil water, you add heat to the water to boil it. So that would be adding heat or gaining energy. So you have to have enough energy to overcome the intermolecular forces in the liquid so that you can break it apart. So the amount of energy that's needed to vaporize a mole of the liquid is called the heat of vaporization, or sometimes the enthalpy of vaporization, or a delta H VAP. So that is how much energy is needed. Have you guys ever seen a water bottle where, like, there's little beads of water at the top, like that? That's what happens when, even if it's not boiling, when you have a closed system or a closed container, some of the liquid will turn into the gas phase, just spontaneously. It'll just happen. But then after a while, there will be a constant rate, and maybe some will turn back into a liquid because there's only so much space in the water bottle above your water, so there's not enough room for all that water vapor, so some of it will recondense into a liquid. So the droplets at the top of the water bottle are the liquid form when the molecules come back together and the intermolecular force pulls them back together. So whenever you have a closed container, there is some vapor pressure in there because it's contained and there is vapor present. But we say when it goes back and forth that it reaches a system at equilibrium, which we use that word in Chem 1 a little bit. So when it's said to be at equilibrium, the system is highly dynamic, meaning even though we can't tell there's change happening, at the molecular level there is change happening. So there's constant turnover from turning from a liquid to a gas and a gas back to a liquid, but there's no net change, so for us it looks like it's stopped. But if we could look in at the molecular level, we'd see that there's a lot of stuff happening. So this is just another example that if you poured some liquid in and capped it, then at first there would only be particles turning into the gas phase. And then after a while, when you have too many particles above the liquid, then some will turn back into the liquid. So vapor pressure happens, it's easiest to see it when you have a closed container and it's above a liquid. Okay. The vapor pressure, like I just said, is the pressure of the vapor present at equilibrium. So these are just some pictures. This picture just shows some different vapor pressures for different liquids. If we had trapped in this tube of mercury, then these are what the original barometers used to look like, because milliliters of mercury. Don't worry, we're getting into vapor pressure in, I think, like 3.4. So we'll talk all about gases in 3.4. Liquids with high vapor pressure are said to be volatile. So this vapor pressure is determined by the intermolecular forces in the liquid. Vapor pressure increases significantly with temperature as well, because with higher temperature, there's more in the vapor phase, so there's more pressure, because pressure comes from collisions. All right, so that's what we're going to talk about for now for the liquid side of things, but now we're going to turn to solids. So just to review, ionic solids have ions at the point of lattice. Just that describes the structure of the solid. So they're very stable, high melting. Probably in our lab we found that they didn't melt on the hot plate. I might have lost to water hydration, so it might have changed color, but it didn't actually melt. And that's because the ionic bond that's actually holding the ions together is stronger than any intermolecular force. The next type is a molecular solid, which has covalently bonded molecules at the points of its lattice. And the forces that holding these together are intermolecular forces, and they depend on the nature of molecules. So whether it's a dipole, whether it's hydrogen bonding, whether it's London dispersion force. And so that's what makes molecular solids so complex and a whole range of different types. Atomic solids all have atoms at the lattice point. They're typically brittle and don't efficiently conduct heat or electricity, and they're formed by strong directional covalent bonds, almost like a giant molecule, because the atomic solids are just having covalent bonds hold them together, not necessarily intermolecular forces. And last but not least, metals, metallic solids. We talked about this before already. They conduct electricity and heat. They tend to be malleable and ductile because of their sea of electrons. And we review interstitial alloys are when you add a different sized, like a smaller sized atom in between the metal atoms. And this will decrease the malleability and ductility to make it more rigid. So, just to kind of see this in picture form, I have is diamond. So this is my in-person structure of diamond. This is the atomic solid, because all it is diamond and covalent bonds that are holding it together. Okay. Then B is sodium chloride. So that, which type of solid would that be? The ionic bond, because sodium chloride is ionic. And notice how there's no like dotted lines or anything like that, so that's your hint that it doesn't have intermolecular forces. And then the last one is ice, which is made out of water, and that would be the molecular solid. So that has, what type of bond, what kind of IMF? Hydrogen bonding, yes. It's holding the waters together.
Okay, so diamond is made of just carbon?
Yep.
Wait, what? It's just carbon?
Mm-hmm. That's all it is. It's carbon. Just carbon and covalent bonds. And sp3 structure shape. Okay, so this is in your notes as well. It's just a good classification of solids. So technically, we have three types of atomic solids: metallic, network, which we're going to talk about in a second, and then group AA. So group AA are the noble gases, which tend not to form solids, but in certain conditions they could, and so that's why they're included there. Molecular solids have discrete molecules like water or CO2 or something like that, and then ionic solids are made up of ions only, so the only bond that's holding them together is an ionic bond. Okay? So, covalent network, or network solids. An atomic solid that contains strong directional covalent bonds to form its giant molecule is the network solid. They're usually brittle and don't conduct electricity or heat. The two most important network solids that we have are made of carbon and silicon. So diamond is the carbon example. Because it's very, very strong. It's only made out of carbon, so it's atomic. Network solids to be a network covalent solid, it's only going to ever contain carbons by itself, or another one, the silicon has something else with it. Now, we saw this in Chem 1, but the diamond all has carbons, and then so does graphite, which what graphite is made out of is carbon as well, but the white tubes are the covalent bonds holding the carbons together. But the green tubes that I have in my picture show the weak bonding between the layers of them. Now, it goes up and down like this just because that's how it's made, but the bonds would actually be in between each layer, like this, okay? Graphite is like what you're writing with your pencil right now, and that's pretty weak because you can break it, and when you are leaving the marking on your paper, what you're doing is you're leaving the sheets on your paper of carbon. The reason why graphite is so much weaker than diamond is because when you have your sheets, the the p orbitals that are pictured here in A for each carbon form pi bonds. So the pi bond is when the tops and the bottoms of the p's combine together. We talked about that already this year. And so it's very, very strong within the sheet because of the pi bonding. But because of the pi bonding, there's no electrons left to really make good forces holding them together. There are no molecular forces holding them together. And so because of that, it's really easy to break the intermolecular force, but it's really difficult to break the covalent bond that's holding together from these pi bonds. So that's why that's why diamond's a lot stronger than graphite. Silicon is the other network solid. It's made up in most things that you find in the Earth's crust. It makes up most rocks, sands, soils. Silicon is there. The fundamental silicon oxygen compound is silica, which has the empirical formula SiO2. So even though technically silicon is known as a network solid, which is technically an atomic solid, the formula, the bare bones formula of it contains oxygens as well. It's not just going to be silicon by itself, it's going to be silicon dioxide, the SiO2, okay? So this is a picture of, this isn't SiO2, but this would be a form of that in that structure. Okay, so the rocks, soils, and clays that we find in the Earth's crust are made up of what are called silicates. These are related to silica, so that other picture I just had was a picture of a silicate, where it may have a different ratio of oxygens to the silicon atoms in the formula of it, but the building block is SiO2, and they're formed in that ratio kind of thing, with even numbers of oxygens. So silicates make up a lot of things, one of which is glass. Most of the time when you just have window glass that's made out of silica that's heated up, has anybody ever witnessed like glass blowing before? It's pretty cool. If you ever haven't, like, do it. It's really neat if you ever have the chance. Where they melt the glass at about 1600 degrees Celsius, and then it's cooled rapidly. They like blow in a pipe, and the amorphous solid that results is called glass. So that's a technical term of a different type of material. But sometimes you almost think of glass as what's called a supercooled liquid, where even though to us we can't see movement, it's thought that the particles are flowing slightly within the frozen glass structure, and so that's why it's called a supercooled liquid.
Isn't glass superheated?
What?
Isn't glass
Superheated what?
sand?
Sand, yeah. Silica sand, yeah.
Oh.
So that's what they melt. They melt it down into making the glass. If it's like a different color than just normal clear glass, then that means that they added different things to it. The glass that we use in this class for heating stuff is called a borosilicate glass. So they actually add boron to it, to the structure, so that it's stronger. If you ever, like when you're cooking at home, do you have like Pyrex? You ever see that word before? That brand is the borosilicate, meaning that it has boron atoms in there as well to make it stronger, so it's more heat resistant. Because if you heat up something that doesn't have that boron in it, it will, when it's cooled down quickly, it will crack. It'll break the glass. So that's one thing. Another thing that's made out of silicates is ceramics. So how many people learned ceramics in class, in school? Yeah, I did it when I was in high school. Ceramics are made of clays, which contain silicates, and then they're hardened by firing at high temperatures. They are strong and brittle, so they do tend to break when you drop a crucible lid. But they are heat resistant, and so that's why we use them for chemistry as well, because they're going to be safe from chemicals that we put in them. But ceramics are very different from glass, because glass is a homogeneous, non-crystalline, almost frozen solution, or that super cooled solution. Whereas a ceramic is heterogeneous. You could actually sometimes see, now in an evaporating dish you might not be able to see it, but like when you're working with clay in our class, you might be able to see different pieces, so that would make it heterogeneous. And we call it's suspended in a glassy cement sort of thing. So a lot of the stuff that we talk about today with all these types of solids, there's a whole category of science that studies these called material science. So chemistry is a part of material science, but they go into so much more detail than what we're even covering in here. So if you're interested in this kind of stuff, that is something that you could study, where you, like, there used to be a Science Olympiad event about material science back in the day, but yeah, this kind of stuff, you don't think about it, but this is related to chemistry too. So there we go.